Hello, in this video I'd like to talk about work and energy and circular motion in mechanics. So the definition of work, also denoted as W, equals to force dot producted with displacement, in which this equals to magnitude of the force times magnitude of displacement times cosine theta. Now what this means is that if this is the force vector and the object traveled a displacement d, then f cosine theta equals to the component of f along the displacement. Therefore, work is simply f along the displacement times displacement. And if force varies with position, let's say force varies with x, then work simply equals to the integral from a to b of the force dx. Now the meaning of work is force times displacement equals to mass times acceleration times displacement from Newton's second law. And displacement equals to v final squared minus v initial squared divided by 2a from the fourth kinematics equation we talked before. So canceling out the acceleration, this becomes 1/2 mv final squared minus 1/2 mv initial squared. So if I define a quantity called kinetic energy as 1/2 mv squared, then work equals to change in kinetic energy. And this is known as work and energy theorem. There's also an energy quantity called the potential energy, which is denoted as U of x. And definition of U of x is negative integral of the force with respect to position. So for example, if the force law equals to negative kx, then the potential energy equals to negative integral of minus kx dx, which is 1/2 kx squared. Or even simply, the force of gravity, if I call the vertical axis as y, equals to negative mgy. This y hat means it's like a unit vector along the y axis, and it has a negative sign because force of gravity is pointing downwards. So therefore, the potential energy equals to negative integral of minus mg dy, which equals to mgy. Now, there are certain types of forces that has potential energy and certain forces that do not. Forces that has potential energy is called conservative. An example of conservative force is the force of gravity. But the force that does not have potential energy, this is called non-conservative. And the prime example of this is force of friction. Reason why force of friction is not a conservative force is that, for example, for gravity, if I bring an object from point A to B, this gains potential energy, and if I bring this back, this should lose potential energy. And since energy is gained, since potential energy is gained, kinetic energy is lost, and since potential energy is lost, kinetic energy is gained. However, for force of friction, if I move an object from point A to B, this loses kinetic energy because force is opposing motion. And when I bring this object from B to A back, this also loses kinetic energy. So there is no gaining back of kinetic energy with respect to force of friction. Therefore, we call it non-conservative. Now, reason why conservative force is called conservative is because energy is conserved. Remember, work equals to change in kinetic energy, which equals to the integral from position A to B of f dx. And change in potential energy equals to U of B minus U of A, which equals to negative integral of A to B of f dx. So therefore, change in kinetic energy plus change in potential energy equals to the integral from A to B of f dx minus the integral of A to B f dx, which equal to 0. So therefore, the total amount of energy, which is denoted as E, is conserved. And this is conserved if and only if force is conservative. So therefore, the work done by a conservative force, if I define work as change in total energy, equals to 0. Meanwhile, the force of non-conservative force, which is change in total energy, is not necessarily zero. Let's look at some example. Let's say there is an inclined plane of angle theta and distance d, and there is mass m, which is at rest. And when this mass is given a slight push, this would slide down to the inclined plane, and this would stay at rest at distance d. Drawing the force diagram of this mass, there's the weight mg pointing downwards. There is the force of friction that is parallel to the distance, but that is opposite to the displacement vector, since displacement vector is pointing this way. And there is the normal force that is perpendicular to the surface. Now note that the normal force dot product with displacement vector equals 0 because theta equals 90 degrees and cosine theta is thus 0. So therefore, we can only think of the work done by friction force, because for conservative forces, change in energy is 0. So the work done by friction, which equals to force of friction dot product with displacement, which equals to negative the force of friction times distance, as they are opposite to each other, and cosine 180 degrees is negative 1. This equals to change in total energy, which is negative mgy. Now, the reason why change in energy is negative is because the kinetic energy remains the same. They remain at 0, since at the both initial and final state, the object isn't moving. However, the potential energy is lost as this object went down a height, and this became sort of like more stable in a sense. And since y using trigonometric identity equals to mg sine theta times d, the force of friction equals to mgd sine theta divided by d, in which canceling off this becomes mg sine theta. Now there is force of gravity, which is also a function of position. So the force of gravity with respect to the distance, which I'm going to denote it as r, equals to negative some constant g times m1 m2 over r squared. Now this constant g is called the gravitational constant, and its value is 6.67 times 10 to the negative 11 meter cubed kilogram inverse second to the negative second power. Now, because this gravitational constant is so small, this is reason why people say gravity is one of the weakest force. Because if you imagine two objects both having the mass of 1 kilogram that is separated by 1 meter, the gravitational force equals to negative 6.67 times 10 to the negative 11 newtons, which means the acceleration equals to 6.67 times 10 to the negative 11 meter per second squared, which is totally negligible. And also, the reason that there is a negative sign for the force of gravity is that this is an attraction force. And if I set the axis of r as pointing outwards, the force of gravity is going towards the negative r direction. Now, force of gravity is conservative because this is a function of position. And the potential energy u of r equals to negative integral of force of gravity dr, which is negative integral of minus g m1 m2 over r squared. Canceling out the r sign, this becomes negative g m1 m2 times integral of minus 1 over r squared dr. Now note that the derivative of 1 over r equals to negative 1 over r squared, because this equals to r to the negative 1 power. So therefore, this integral just simply becomes negative g m1 m2 over r. And this is the potential energy function of gravity. So if the object is going under a circular motion, in which this is different from rotational in a sense that rotational is object rotating and circular motion is object going in circles, is that there is a centripetal force that is applied in the radial direction. So for example, let's say an object M is rotating around this point with distance r. Then the definition of centripetal force equals to negative mv squared over r, in which there can be the net force can point in any direction. Let's say it can point at this direction, and this travels along that way. Then the radial component, which would be F, like cosine theta, should equal to mv squared over r. And again, reason why the centripetal force is negative is that it is pointing inward. Therefore, it is pointing the negative r direction. Now then one might ask, what happens to the perpendicular component of this force? Then the perpendicular component of this force, which in this case it will be F sine theta, this is simply just mass times acceleration. This just increases the speed of v in this circular motion, while the radial direction, which again does not do work since the displacement and the force vector is perpendicular, this force is acted to keep this circular motion, and that's why it is a function of velocity. Now let's look at the circular motion of the Earth and the Sun. Let's say there is Sun with mass m and Earth with mass small m. And we're assuming that the mass of the Sun is much greater than the mass of the Earth, such that the mass of the Sun just stays the same, like it does not move around the Earth. Then the force of gravity equals to negative g small m big M over r squared, where big R is the distance between the two planets. And force of gravity must equal to the centripetal force, since our Earth goes around the Sun in a circular path, and therefore this should also equal to negative mv squared over r. Now putting this expression and evaluating them, I can cancel out the r and cancel out the mass, and therefore v equals the square root of gm over r. Now therefore I can calculate the kinetic energy of the Earth, which is 1/2 mv squared, also which is equal to 1/2 gm big M over r. Now remember that potential energy, this equals to negative gmm over r. Therefore, if I add these two up, then the total energy is simply negative gmm over 2r. Now notice that this mathematically turns out to be negative of kinetic energy, which is not that common, but it is one of the interesting features of planetary motions. Okay, so I've prepared several problems from the F equals MA exam that is related to work and energy, circular motion, and even planetary motion. And the first one is from 2016, number 9. So a small mass m is placed on a sphere with diameter d, and is asking what is the velocity of this mass when this leaves the surface. Now, a very important point to notice is that the normal force is equal to 0 at the instant the bead leaves the sphere. This is because when this leaves the surface, there is no pressure that is exerted from the surface to the mass, and that is why the normal force should equal to 0. And if this mass, m, leaves at angle theta to the vertical, then the only force that is applied is the force of gravity. And since this mass is under a circular motion, the radial component of gravity should equal to the centripetal force. Therefore, mg cosine theta, since this angle is also theta, equals to mv squared over r. And solving for v squared, I get v squared equals gr cosine theta. And since radius is half of diameter, this equals gd cos theta over 2. Now, I can also use conservation of energy since this sphere was frictionless and there is no non-conservative forces. And the height that this mass went by is r times 1 minus cosine theta. And this is because if I draw out the circle, this initially started at height r, and then the final height is r cosine theta. So therefore the difference in height is r minus r cosine theta, and solving for r, this is r times 1 minus cos theta. Therefore, since energy is conserved, change in kinetic energy should equal to negative change in potential energy. Therefore, 1/2 mv squared equals to mgr 1 minus cos theta, which is mgd over 2 times 1 minus cosine theta. And solving for v squared, I get v squared equals to gd times 1 minus cosine theta, which again from here equals to gd times cosine theta over 2. Now if I solve for cosine theta initially, I get 1 minus cos theta equals to 1/2 cos theta, in which cosine of theta becomes 2/3. Therefore, plugging in this cosine theta to either of the v squared value, I get v equals to square root of GD over 3, in which, looking at the answer choice, it is E. So the next question is about power, in which I'm going to talk about it right now. So definition of power is rate of change in energy with respect to time. And since change in energy equals to force dot product with displacement, if I divide this with time, this term right here becomes velocity. So therefore, power equals to force dot product with velocity. Now looking at question number 11, it says a car that looks like a cube has size of S, and this has a uniform mass density. So therefore, mass equals to density times volume is proportional to S cubed. And when this travels at the speed v max, there's going to be a force of friction that opposes this vehicle. And power of this frictional force equals to negative force of friction times velocity. This is because the dot product between the force and velocity is negative since they're opposing each other. Therefore, the power output should cancel out the power from the friction, because this should keep this car at a constant velocity, in which this should have net power of 0. So therefore, the power output equals to force of friction times V max, which is proportional to AV squared times V, which is AV cubed. Now, since area equals to S squared, I can claim that power is proportional to S squared V cubed. Now, reading this problem, the problem also said the power output is proportional to the mass, in which previously I said mass is proportional to S cubed. So therefore, S cubed should be equal to S squared times V cubed. So canceling out the S term, V equals to S to the power of 1/3. And since mass is proportional to S cubed, S is proportional to M to the power of 1/3. And therefore, plugging this relation to here, I get V max proportional to S to the 1/9 power, in which, looking at the answer, it would be answer choice A. So the next problem is on circular motion from 2017 F equals MA question number 1. So there is a circular track that looks like this, and the motorcyclist is riding on this vertical track, and therefore the force diagram of this motorcycle would be, there would be the weight that is pulling the motorcyclist down, and normal force, in which this is going to be our centripetal force, as this is the only force that is exerted on the radial direction, and there will be the force of friction that is going to hold this motorcyclist up. Since the normal force equal to the centripetal force, this should equal to mv squared over r, and since the problem said the motorcycle speed is s, this is going to be ms squared over r. So therefore, since the net force along the vertical direction should be 0 from Newton's second law, mu times ms squared over r, or mu times Fn equal to friction, should equals to mg. And canceling out the m, this become, and solving for mu, I get mu equals to gr over s squared. Now, since gr is constant, we can conclude that mu is proportional to s squared, in which, from the problem, it would be answer choice D. The next two problem is also about power, just like the previous problem. So question number 7, it says there is a train of mass m, and this mass is increasing at a constant rate of rho. So therefore, the kinetic energy as a function of time is 1/2 m of t v squared. Now, since v is constant with respect to time, we don't need to worry about v varying with respect to time. And this would be 1/2 m plus rho t v squared. Therefore, if I take the derivative of the kinetic energy with respect to time, only term that varies with time is rho t term, and this is linear with respect to time, so I can just take the coefficient of this term, which would be 1/2 rho v squared, and therefore the rate of change in kinetic energy would in this case equal to d. Number 8 is also a similar question in which this is asking what is the power of this engine. One might think that power equals to rate of change in kinetic energy, but this is not necessarily true, as I'll prove why. So the definition of force, while in Newton's law we said F equals ma, this is only true when mass is constant. But when mass varies, the definition of force is actually the time derivative of this quantity called mv, in which we're going to talk about this quantity mv, also known as momentum, on the next video. But taking this derivative from using product rule, this is dm dt times velocity plus m dv dt. And therefore, when mass is constant and dm dt is 0, force equals to ma. But in this case, velocity is constant, so therefore force equals to dm dt times velocity, in which since rate of change in mass equals to rho, this equal to rho v. So therefore, so when this train is going at speed v, like the force that is applied is opposing the velocity. So the power of this force is negative rho v squared, because when masses are added, this is going to bog down the train. So therefore, the power output from the engine should cancel out this power, negative power, which equals to rho v squared. So therefore, looking at the answer choice, it is going to be E. Now then, one question that one might ask is, if the power output from the engine equals to rho v squared and change in kinetic energy equals to 1/2 rho v squared, this means that only half of the power is used to keep up to the increase in kinetic energy. Then the question is, what happens to the rest of the half? The rest of the 1/2 rho v squared is actually dissipated as heat. And this heat is a result from the force of friction between the snow and the train. Now, reason why I'm saying this as heat is that for an object that moves on a surface with friction, then energy is lost from the work done by the friction, and that energy is lost as form of heat. And in this case, the collision of the snow particle with the train surface is going to dissipate the energy from the engine as heat. Now the next question is 2018A, question 6. So in this problem, there is a mass on the inclined plane that has a mass of 115 kilograms, and this distance of the incline is 5 meters. If a person applies a force of 1,000 newtons parallel to the surface, and there is a force of friction equal to 400 newtons, then the question is asking, what will be the speed of the mass when this reaches the end? I'm going to use the work-energy theorem, which the non-conservative force dot product with displacement equals change in energy. In this case, the net force equals to 1,000 minus 400 newtons, which equals to 600 newtons, and the displacement equals to 5 meters. And since this net force of 600 newtons is pointing upward and displacement is also placing upward, the cosine theta would become 1. So therefore, the work would be 600 newtons times 5 meters, which would be 3,000 joules, in which joules is the unit of energy, which would also be kilograms times meter squared over second squared. And this 3,000 joules is going to be change in energy, which would be 1/2 mv squared, because initial kinetic energy was 0 and it gained kinetic energy, plus mg times 5 meters times sine of 20 degrees. This is because this went up a height of 5 meter times sine 20, and therefore the gravitational potential energy is just going to be mgh. And plugging in the numerical values, this would be 1/2 times 115 kilograms times velocity squared plus 115 kilograms times 10 meter per second squared times 5 meter times sine of 20 degrees. And therefore, solving for v here by plugging into the calculator, I get v equals to roughly 4.24 meter per second, in which A would be the answer. So, and the next question is about planetary motion, and it is asking the total energy has decreased by 1 joule from the air friction, and it is asking what happens to the kinetic energy. Now, remember what I said previously, kinetic energy, which equals to 1/2 mv squared, happened to be gmm over 2r, and gravitational potential energy is negative gmm over r, which leads to total energy becoming negative gmm over 2r, which is also negative of kinetic energy. So therefore, when total energy decreased by 1 joule, then kinetic energy should be increased by 1 joule. So therefore, in this case, the answer will be A. So the next problem is question 18. So in this case, there is a mass attached to a rod. And then it is asking what is the difference in tension between when the mass is upward and mass is downward. And it is assumed that there is no friction, or there is no non-conservative force, because this mass is keep on going through the same motion periodically. Using conservation of energy, and if I call this velocity as v naught, and if I call this velocity v final, then 1/2 v naught squared plus 2 mgl, since that is the potential energy difference between this state and that state, should equal to 1/2 mv final squared. And also, since mass is going through a circular motion, drawing the force diagram, when the mass is upward like this, the weight of this mass is pointing downward, so as the force of compression or the force of tension. In this case, the mass is pointing downward while the tension is pulling upward. I'm going to call this T1 and that T2. So from here, T1 plus mg, which is the net force along the radial direction, equals to m v naught squared over L. So therefore, T1 equals to mv naught squared over L minus mg. Similarly for this case, since these two forces are opposing each other, T2 minus mg is the net force along the radial direction, in which this equals to mv final squared divided by L. So therefore, T2 equals to mv final squared over L plus mg. So if I take the difference between those two tensions, so T2 minus T1, this would be mv final squared over L plus mg, subtracted by mv naught squared over L minus mg. Now from here, I'm going to plug in the value from here to here. Now, using the equation from conservation of energy, which was 1/2 mv naught squared plus 2 mgl equal to 1/2 mv final squared, I'm going to cancel out the 2 and times it by 2 and divide this by L, which this is going to cancel, and this is going to lead to mv final squared over L equal to mv naught squared over L plus 4 mg. So therefore, the difference in tension, this is going to be mv naught squared over L plus 4 mg plus mg subtracted by mv naught squared over L minus mg. And this term would cancel out, and this would become 6 mg, in which from the answer, this is C. So the last question is from 2018B, question 24. There is 2 methods for this problem. One is taking an infinitesimal force and integrating it, and the other is using pressure. And I'm going to show both ways for solving this problem. So on this problem, there is mass m and this hemisphere with radius r. And it is asking what is the gravity that is exerted from the hemisphere to the small mass if the mass surface density is sigma for this hemisphere. So for taking an infinitesimal force, I'm going to call this infinitesimal area that is around like a belt of this hemisphere as dA. And the infinitesimal force of gravity equals to negative gm dm over r squared times cosine phi, where phi or phi is the angle from the vertical like this. Reason why I'm taking cosine phi is because the force of gravity is exerted along this way, and from symmetry the horizontal component is going to be canceled out, therefore the vertical component would remain. And the vertical component is using trig identities equal to cosine phi of the magnitude of this vector. And dm, which is the infinitesimal mass of this area, is simply sigma times dA, since sigma is just mass over area. Now what I am going to do is I'm going to solve dA with respect to phi. Now dA, if I kind of expand this is going to have thickness of r times d phi, because this length, this thickness here is just an arc with angle d phi. So therefore this thickness is r times d phi. And the length of this is simply the perimeter of this circle with radius r sine theta, in which this case this is 2 pi r sine theta. So therefore dA equals to 2 pi r squared sine phi d phi. So if I plug this value to the infinitesimal force equals to negative gm sigma over r squared cosine phi times dA equals to negative gm sigma over r squared cosine phi times 2 pi r squared sine phi d phi. R squared is going to cancel out, and this would become negative pi gm sigma times 2 cosine phi sine phi d phi. Now this from trig identities becomes sine of 2 phi, in which this infinitesimal force equals to negative pi g sigma sine 2 phi d phi. Now the final step is integrating this. Force equals to the integral of df equals the integral of minus pi gm sigma sine 2 phi d phi. And the range of this integration is going to be 0 to pi over 2, since it is going to start at 0 degrees and end at 90 degrees, which is pi over 2. Now solving this integral, since this is a constant, I'm going to bring this out, which is going to be minus 2 gm sigma. And the integral of sine 2 phi is going to be negative cosine 2 phi divided by 2 from 0 to pi over 2, which would be pi gm sigma times cosine of pi minus cosine of 0, which is going to be 0 divided by 2, which is going to be pi gm sigma. There's going to be a minus sign, but this minus sign we can kind of neglect it. So therefore, after this heavy and convoluted integral, we conclude that the answer is E. So the second approach is using pressure, in which definition of pressure is force divided by area, and in this case this is gm times big M, which is the mass of the hemisphere, over r squared times area. And this mass over A, this term becomes gm sigma over r squared. Now, I'm going to talk about fluid dynamics later, in which I'm going to talk about pressures and velocities of a fluid. But in air, as long as the air density isn't too high, the pressure along this hemisphere is going to be same as the pressure on this mass, or pressure on this surface. So therefore, force equals to pressure times the surface area equals to pressure times pi r squared in this case, since the surface area equals pi r squared. And therefore equals to gm sigma over r squared times pi r squared. And canceling out the r squared, this equals to pi gm sigma, in which this matches to our previous answer with the integrals.